Hello everyone, and welcome to Module 4, Methodologies and Recommendations for Adaptive Management in the Black Sea. This module has been created within the BridgeBS project. My name is Stefano Menegon, and I'm a senior researcher at CNR-ISMAR, the Institute of Marine Sciences of the Italian National Resource Council. The aim of this presentation is to introduce the methodological innovations and the new decision support tools, illustrate how they have been applied within the BridgeBS project, and present the resulting findings along with recommendations for adaptive management in the Black Sea region. After my contribution, other researchers and colleagues will present the different thematic aspects and methodologies of the process. Let's begin with a quick overview of the structure. As you can see here, Module 4 is organized as a process, visualized as a sequence of interconnected blocks, representing the steps that link scientific analysis to adaptive management and policy making. The module is structured in 5 main components: adaptive management, which provides the conceptual foundation and framework for continuous learning and adjustment; an integrated machine learning and artificial intelligence-based risk assessment framework, which supports the analysis of environmental risks in a data-driven way; the cumulative effect assessment tool, which helps quantify and visualize the combining impacts of multiple human activities and environmental pressures; the analysis of future scenarios, using the CA tool to explore how different management options or policy choices could influence marine ecosystems over time. And finally, we will discuss recommendations for adaptive management, planning, and policy implementation, translating the analytical outcomes into actionable guidance for decision makers. Together, these elements illustrate how data, models, and decision support tools can be integrated to strengthen adaptive management in complex marine and coastal systems like the Black Sea. Before diving into details, let's see the context. This module focuses on the Black Sea, both at a basin-wide scale, but also across 3 pilot sites at country level. The Black Sea is a unique and complex system, semi-enclosed, high productive, and subject to multiple human pressures. The key challenge here is to promote the sustainable management of such a dynamic environment where natural and human processes interact across multiple scales. To address this challenge, our strategy is to perform a multi-stressor analysis of risk and impact in order to develop adaptive management strategies and policy recommendations. And now, before exploring the tools and the analysis in details, we will take a step back and introduce the concept of adaptive management, which is the frame which provides the framework of this entire module. So what is adaptive management? Adaptive management is a continuous, systematic process through which we learn from experience and adjust our actions accordingly. It recognizes that management decisions are always taken under uncertainty and therefore must remain flexible and evidence-based. In practice, adaptive management follows a cyclical, iterative process, often summarized as plan, act, monitor, evaluate. Each cycle builds on the lessons learned from previous steps, allowing decision makers to refine strategies and improve outcomes over time. In marine and coastal management, this approach is particularly relevant because conditions change constantly due to climate variability, new human uses, technological developments, and evolving societal priorities. Adaptive management is also about balancing sustainability dimensions, environmental, social, and economic, which are interlinked in hierarchical relationship. Healthy ecosystems support societies, and societies sustain economies. According to Barnard and Elliott, there are 10 key tenets that we can use to investigate and sustainable environmental management, such as maintaining ecosystem structure and function, promoting resilience, engaging stakeholders, interacting knowledge across disciplines, and ensuring transparency and accountability. Adaptive management embodies this principle by turning sustainability goals into a dynamic process of continuous improvement. So, how can adaptive management be operationalized in the marine context? One of the most effective frameworks is maritime spatial planning, MSP. MSP is defined as a practical way to create and establish a more rational organization of the use of marine space and the interactions between its uses. Its goal is to balance demands for development, such as offshore energy, tourism, or transport, or fishery, with the need to protect marine ecosystems and to achieve social and economic objectives in a transparent and participatory way. The relationship between adaptive management and SRP is very close because adaptive management provides the philosophy and process, a learning-based iterative approach, while MSP provides a framework and tools for putting into practice the spatial and policy level. Finally, to make adaptive management and MSP truly effective, we need decision support tools, DSTs. DSTs are software-based instruments that help ensure that decision-making is systematic, objective, and transparent. They allow us to integrate scientific data, modeling results, and stakeholder knowledge into policy processes. Users of DST can include policymakers and planners, scientists and researchers, industry representatives, and NGO or practitioners involved in marine management. In the following sections, my colleague will guide you through how we apply machine learning, AI-based risk assessment, CEA, cumulative effect assessment to support adaptive management in the Black Sea, and how these results feed into policy recommendations for sustainable ocean governance.
Hi, my name is Philip Smith. I'm from the Technical University of Denmark, and I've recently completed my PhD under the Bridge BS project, where I've been working on AI for environmental and ocean modeling. In this recording, I will be presenting this section on integrated machine learning and artificial intelligence-based risk assessment framework, and how these tools can help support decision-making. Okay, but before I go into details, I want to just briefly clarify what I mean by AI, machine learning, and deep learning. So artificial intelligence, or AI, is the general field of making computers solve complex tasks in a way that mimics human decision making. A classic example of that would be old chess programs or other early rule-based expert systems. And then we have machine learning, which is a subset of AI that focuses on learning patterns directly from data instead of from handcrafted rules. A simple example of that could be a spam filter trained on labeled emails. And then finally, we have deep learning, which is a specialized type of machine learning that uses these neural networks with many, many layers that all learn different patterns and structure directly from raw data, which is why they can recognize things like faces in photos without us defining what features to look for, such as eyes or noses or stuff like that. Okay, but when we study the ocean and Earth system processes, we rely on huge and diverse environmental data sets. So the question then becomes, what can AI and machine learning actually help us do with all of this? Deep learning can actually help us make a lot of sense out of all this information by learning patterns directly from large multi-source data. It becomes a very powerful tool in understanding and predicting different ocean behaviors. One example could be satellite or sensor data. So, for example, automatically detect or classify patterns in data, such as ocean currents if they're changing, if you have algae blooms coming, if there's an oil spill, or where you have cloud formations. Then it can also help improve ocean and climate forecasting. So kind of complementing already established numerical models, we can have deep learning models learning the relationships between different climate variables, and in that way get an even more accurate and improved short and long-term predictions. Then it can also help us monitor environmental changes. So, for example, automatically track sea level rises, glacier retreats, coral bleaching, or deforestation. It can also help us understand biogeochemical and physical processes, the interactions between the atmosphere, ocean, and some land components. In that sense, it can help us better understand carbon cycles and ecosystem dynamics. It can also support autonomous ocean exploration. So, for example, if you have underwater robots or drones, which are collecting different kinds of data, such as sonar, different visual or acoustic signals, you can use deep learning to try to also run through so you don't have to manually inspect all of these, but also find interesting patterns in the data. And that kind of brings me to the last point, which is that deep learning is also very suitable for combining different types of data. So, for example, satellite data, local measurements, process-based model outputs. Here we can use deep learning to actually learn from all of them and see if there's some trends we otherwise wouldn't have found. And that brings us to the main part of what I've been looking into and what we will be showing here. So these are the emulators of Earth system models. So traditional process-based models and Earth system models are all extremely powerful and a good way of understanding the dynamics of different regions. But they can also be incredibly expensive to run, especially if you want high resolution, if you want long time periods, or if you want several many different scenarios for testing. In that sense, in such scenarios it can be very beneficial to use an emulator as a complement. And in our case, when we say emulator, we mean a neural network that we have trained to learn the behaviors of these simulations. So what we do is that the network learns patterns and relationships between variables directly from the simulation data, and then it learns to reproduce them. So it learns by example, by showing a lot of simulation data, it then tries to reproduce what it's seeing. And then once trained, they can very quickly predict how the system evolves under different input conditions or different scenarios. So here the main advantage of these emulators is the speed. So these emulators can reproduce complex dynamics at a fraction of the computational cost of the original simulations. And especially this lets us do a lot of what if scenarios. So if we change different variables, if the temperature goes up or if the currents are changing, we can very quickly test what effect that would have. We can also analyze the emulator once it's trained to see what variables or what regions have the biggest influence on the ecosystem and the ecosystem changes. This helps us also build early warning indicators for extreme events or sudden shifts, so we can kind of analyze what is coming before we have an extreme event, where to look and what to look for. Finally, it can also help us highlight potential regime shifts. So by showing how the ecosystem states may change over time and highlight where especially it's changing. Okay, so in short, emulators don't replace traditional models, but they can be a very efficient complement. They can give us fast forecasts, rapid scenario testing, and a better understanding of the key drivers of the system. Okay, but here, if we look to the right, we see kind of the framework of how we trained our neural network emulator. So we had a simulation called the Nemo Bambi simulation, and then we used most of this data to train a network. So here we had some training data that the network is seeing, and it's trying to reproduce if you have a certain amount of input days, then how would the system evolve of the next days? And the system then learns and iteratively updates to try to reproduce the input as best as possible. Once it has been trained, then we test it on a separate, very similar data set to see can it also reproduce what it hasn't seen before. And once we're satisfied, it brings us to the next part where we can actually use the model under new initial conditions and different states, different scenarios and projections. So, for example, it can help us see what drives the changes in the ecosystem and where it's most vulnerable. It can improve how and how early we can spot and predict things like storms, blooms, flooding. Uh, can also automatically pick up different important features in the data like pollution plumes, temperature fronts, or changes in chlorophyll patterns. It can give us more accurate predictions, which just in general help with better risk management, mapping, and to make better decisions. And finally, it gives us a tool that can actually be used for better coastal planning and resilience, where you can actually test different scenarios, see what impact it has on the system, and do it very rapidly. So go even more into detail with what we did. So this is the specific emulator setup we have been using. So on the left, we have sequences of images of the Black Sea of a wide range of different variables. So we have physical and biogeochemical variables, temperature, wind, salinity, sea surface height, different nutrients. All of that we give as an input. Then we use what is called an encoder-decoder structure. So essentially, what the encoder does is that it compresses the very high dimensional input space into the most important trends and dynamics, which are useful for the future evolution of the system. And then once it has done that, it then here in the ink decoder, then use this compressed version of the input to turn it into actual forecasts. So that is what we see on the right, where we see how the output would be. So for example, we have maybe the last month of different variables as input, and then as output, we see how does the system then evolves over the next coming weeks. And this is then we have for the whole Black Sea. But what we then can also do is also zooming in on different parts of the Black Sea and see how well it predicts in these regions. And here we can see 4 different places in the Black Sea. In the middle, we see the blue is the actual model we have been trying to reproduce. The red is our emulator, and the green is the climatology. So how the chlorophyll normally looks in that region in that period. And we see, although sometimes the peaks are not fully captured by the emulator, that almost all the time it performs very well in predicting how the chlorophyll will look in the future, which is very nice to see how well it actually can reproduce what it has seen. And that brings us then to the next point where we can then analyze the emulator and see if the drivers are different for different regions. So here on the plot to the right, we have 2 columns. The first column is the short-term predictions, so just the next couple of days. So what drivers are important for that? And then we have for the slightly longer term, which is 11 to 15 days in the future, are the input drivers different? And we see that actually there is quite a significant change. And we see what stands out is that the main drivers aren't the same everywhere. So they're quite different in different regions. Each region responds differently to changes in the input. We see that some areas are dominated by light in the short term, while others are more influenced by nutrients or physical conditions over a longer lead time. This really shows us how the emulator can pick up more region-specific drivers of chlorophyll dynamics. So in that sense, it doesn't just give us predictions, it actually helps us understand why things are changing in parts of the basin. And then to conclude, emulators give us a fast and efficient way to turn complex ocean science into practical tools. They let us capture dynamics, run quick forecasts, and explore what-if scenarios that would otherwise be very slow to do with a full model. They also naturally fit into initiatives like the digital twin of the ocean. Here, the Black Sea is a really good example, but the same approach could work in many other regions as well. And overall, we have shown that emulators supports both risk assessment is beneficial for early warning systems, and in that sense, it can really help to do better decision making in the future.
Hi everyone, thank you for tuning in for this Mooc. My name is Sofia. I'm a PhD student at the Institute of Marine Science of CNR and the University of Venice. And today I will talk to you about cumulative effects assessment tools developed as part of the Black Sea project. So to start, before we talk about cumulative effects assessment tools, we need to understand what we mean by cumulative impacts or effects and why it is important to study them in the context of maritime spatial planning and marine management. So as we all know, humans carry out a series of different economic activities in the sea, such as fishing, transport, aquaculture, tourism, extraction of energy, etc. And it's becoming clear that these activities can have negative impacts on marine species and habitats. And these impacts may look negligible if taken individually or at a specific time or place, but what happens when you take them all together? They may have global repercussions, like a death by 1,000 cuts. And that is what we mean by cumulative impacts. So this in the yellow box is one of the accepted definitions, and it states that cumulative impacts are those resulting from the successive, incremental, or combined effects of an activity when it is added to all other existing or planned ones. But how can we evaluate or quantify cumulative impacts? First, we need to identify what is known as the impact chain, and that is the link between these three variables, so the human activities generating certain pressures or effects which are impacting environmental components. By combining quantitative and spatially explicit data on these three variables, we can obtain maps of cumulative impacts like the one shown in the slide here. And this is a global map, and it actually comes from the creator of this methodology, which was first published in 2008 and has since then been widely used in support of MSP and marine management in general. So we can think of it as a decision support tool, or DST. In the Black Sea, we adopted a very similar methodology to perform a risk-based cumulative effects assessment on 4 different regions. So we had 3 regional case studies, which you see on the left of the slide here, and 1 basin-wide case study, so considering the Black Sea as a whole. We collected over 110 data layers, describing the 3 variables that I was mentioning before, so the human activities, pressures, and environmental components. And we had 3 teams of local experts involved supporting us in the analysis. The final goal was to identify hotspots of cumulative impacts on target environmental components and ecosystem services in the Black Sea to eventually support the development of adaptive management measures in present and future scenarios. So to conclude, I would like to show you the type of results that the cumulative effects assessment produced. The main result is these kinds of maps showing the spatial distribution of the cumulative impact score. So for each pixel, you have a score of cumulative impact, and this helps spatially identify the hotspots of impacts and does inform spatial planning. But the cumulative impact score can also be disaggregated to form heat maps like these, showing, for example, the contribution to the total cumulative impact score of each activity environmental component pair. And in this section, I will talk about the analysis of cumulative impacts on future scenarios that we performed in the Bridge Black Sea project. Like in the previous section, we start with some background. In particular, why do we look at future scenarios in maritime spatial planning? So when we talk about future scenarios, we're talking about imagined or projected versions of the future, which can differ from each other, for example, in terms of their likelihood to happen, like the futures cone is showing. Plus, MSP is by definition a future-oriented activity, because within MSP we make decisions on the use of the maritime space to reach a series of objectives. Essentially, we are trying to answer the question of where we want to be. In addition, we now also have to deal with the effects of climate change, which requires some preparation and adaptation. So by exploring and analyzing these different versions of the future, we can develop solutions to problems that we expect will arise. So it can be useful to combine this idea of future scenarios with the analysis of cumulative impacts that we talked about in the previous section. And performing a CEA on a future scenario can be helpful because it allows decision makers to prioritize potential management measures based on an expected future. We can compare the present CEA with the future one to analyze spatial and temporal variations of risk. And by doing so, a cumulative effects assessment on future scenarios will also highlight the level of success of different management measures, for example, by showing an increase or decrease in cumulative impacts, thus supporting adaptive management. In the Bridge Black Sea project, we took the same 4 case studies that we analyzed in the present situation, so 3 pilot sites and 1 basin-wide case study, and we developed future scenarios for the year 2050. To build the scenarios, we used climate projections of different ocean variables, whether physical, biogeochemical, and ecological. But also we took into account the visions and expectations of local stakeholders and local experts for a desired future in their region. Based on all of this, we came up with different maps in each pilot site, identifying regions where future developments in different maritime activities would occur. So in the 3 figures here, you see the 3 regional pilot sites, and each polygon of a different color represents an expected development in one of the maritime activities shown here in the legend. Since the methodology was the same as the one we used in the present condition, the same kind of results were obtained. For example, the map of cumulative impacts for the year 2050. And we can compare that with the present condition, for example, by calculating the percentile difference. So here the brown areas represent an increase in cumulative impacts and the dark blue areas represents a decrease. Of course, a decrease in cumulative impacts is what we want since we are trying to represent desired scenarios. By aggregating the cumulative impact score by the different type of activities or by the environmental components, we can have a better idea of which management strategies adopted in the scenario resulted in a positive outcome, so in a lower cumulative impact score. For example, in the Bulgarian pilot site, a strong reduction in industrial fishing, which is the blue boxes in the bar plot, and maritime transport would significantly reduce cumulative impacts in 2050 compared to 2020, particularly on fish species of commercial value.
Hello everyone, I am Teodor Musat from GeoEcoMar, Romania, and I will continue with recommendations for adaptive management, planning, and policy implementation. So recommendations are a pool of action proposed to be carried out for achieving the objectives. The goal of these adaptive management recommendations, which are important both within the country and across borders, is to have a real impact at the social and policy level by changing the current dogma of management practices which often lack long-term vision and coherence. The proof concept of this idea of integration of science, society, and policy that makes possible informed and flexible decision-making processes which define any successful adaptive management plan. Recommendations can contribute to policymaking in research, nature management, innovation and technology, ongoing and future MSP processes, and the planning of action to achieve the goals of the European Green Deal agenda. Enhance science policy dialogue and stakeholders' participation at the decision-making processes, and trigger and sustain business opportunities. The recommendation could be area-based recommendation that could refer to the Black Sea as a whole or selected pilot sites. Ecosystem-based recommendation referring to the core system services in the select area, and blue economy sector-based recommendation referring to the relevant blue economy sector. So, ambition and challenges. The ambition is to have a real impact at the social and policy level by changing the current dogma of management practices, which often lack long-term vision and coherence. Challenges in elaborating comprehensive recommendations are related to insufficient data, having a clear picture of the current conditions in several social economic sectors or ecosystem services, or people's reluctance to actively get involved in the decision-making processes, low confidence in prediction of ecological phenomena and ecological indicators evolution. And the last one is limited resources and tools to improve the current management at several levels. The development of these recommendations are made in the simple four phases. The first phase is baseline, is to set up the scene, define the current environmental, social, economic, and policy situation for each site of interest and the Black Sea Basin as a whole. The baseline phase will provide the information on environmental, social, economic present condition and trends, and existing or planned strategy, including objectives and actions for building an overall picture of each pilot site, which is necessary for conducting successfully the next phases. Gather and update data surveys to build a clear picture of existing conditions and trends. Data and all the information is taken from the scientific publications, national and regional reports, or project reports. The second one is the analysis phase, which indicate critical risk and gaps in current management. The types of input fit this phase: scientific input through experts in their domain, and stakeholders through living labs, questionnaires, face-to-face interviews, etc. In this phase, engage stakeholders to test how effective existing plans are. In this step, use models, cumulative effects assessment, machine learning, and scenarios to understand today's threats and future conditions. The main questions here are the objectives clearly stated, measurable, achievable, result-oriented and time-fixed objectives? Are actions or plan appropriate, feasible, or effective? Or to what extent the selected objectives are accomplished? The third one is the recommendations phase. Develop concrete actions to address current and future risks to be included in the so-called draft recommendations, which will be presented to the stakeholders for consultation. Following their feedback, the draft recommendation will be consolidated through linking each action to ecosystem service and blue economy sectors. At the end, combine this into a clear area-based, economic services-based, and sector-based recommendations that are flexible and practical. And the last one is the synthesis phase that integrates all findings into clear diagrams, flowcharts, and visual tools. Show links between pressure risks, ecosystem services, economic sectors, policies and recommended actions, support adaptive decision-making with easy-to-use tools for stakeholders and policymakers.
As we reach the end of this module, let's briefly recap the main take-home messages. First, sustainable environment management is truly adaptive when it follows a continuous learning cycle, monitoring the effects of implemented measures, learning from outcomes, and adjusting actions accordingly. Second, AI-based emulators are providing the powerful tools to meet societal needs by translating scientific knowledge into actionable insights. They can be easily integrated into the European digital twin of the ocean, as demonstrated in the Black Sea case, and they are particularly effective for testing what-if scenarios and providing short-term forecasts. Third, the cumulative effect assessment helps us understand how multiple human pressures interact in space and time, revealing potential amplified of cumulative impacts on marine ecosystems. It is core part of decision support tool for evidence-based marine management. Fourth, analyzing future scenarios allows us to explore possible pathways under climate change and socioeconomic uncertainty. Within the adaptive management framework, CA applied to future scenarios helps evaluate the effectiveness of management measures and supports the learning by doing process. Finally, the recommendations derived from this analysis aim to guide managers and planners in dealing with uncertainty, helping them respond effectively to the evolving interaction between climate, human activities, and marine ecosystems. All the methodologies, tools, and results presented in this module are fully referenced in the accompanying materials in the project and in the project deliverables. You can explore them further for in-depth study and additional resources. And with that, we conclude Module 4, Methodologies and Recommendations for Adaptive Management in the Black Sea. Thank you very much for your attention and engagement.